Welcome back to Chapter 11. In this lesson, we'll be doing some more detective work. Putting our chapter in context, we've already looked at the logic of hypothesis testing, looked at hypothesis types. Now we'll look at some examples, then level of significance, critical values, critical regions, directional tests, some more examples, and then errors of inference. So we'll look at some examples ahead. Assume a normal population with known standard deviation and unknown mean. Given a random sample of size n with observed mean, we wish to test a null hypothesis of the general form. H sub 0, which stands for the null hypothesis, is mu equal k. So mu, the mean of the population, equals some constant k. And that constant is specified by the researcher. So let's consider a practical problem. Where you may want to test attitudes of a population of college-bound 12th graders. Suppose you have a measure of optimism toward the future, and you know from data in a norming sample that the mean of the optimism scale is 100. Suppose, too, that you want to do some detective work on a subset of the entire 12th grade population, specifically the college-bound population, and you have a hunch or hypothesis that this population of college-bound students have a mean optimism score equal to the larger population mean of 100. We don't usually know the mean and standard deviation of the population at large, but for purposes of this example, let's imagine that we do know these parameters and the mean is 100 and the population standard deviation is 15. You then collect data on a sample of 25 college-bound 12th graders at your school and find the mean of the sample equals 103. You observe a 3-point discrepancy between the mean of the sample and the hypothesized mean of the population. Is a discrepancy of at least that magnitude possible due simply to sampling error? Well, yes, of course, it's a possibility. Is a discrepancy of at least that magnitude likely due simply to sampling error? Well, we need to do some mathematical detective work to answer this question. So, example 1. In order to answer the last question, we need a picture or a model of the means of all possible samples of size 25 from the proposed population. And we have such a model, the sampling distribution of the mean, which we've seen many times before. The hypothesized sampling distribution has a standard deviation of population standard deviation divided by the square root of n. And you plug and chug and out spins the answer 3. That is the standard error of the mean. Now we can picture the sampling distribution with a mean of 100 and a standard deviation of 3. Where are the samples whose means differ from the hypothesized population mean by at least as much as our sample seems to? Notice we have to think of the distribution as a symmetrical creature. So we have to consider not just the sample means that live at least 3 points above the mean, but also the sample means that live at least 3 points below the mean. So we're looking at those samples with a mean of 100 plus 3 equals 103 or higher, or a mean of 100 minus 3 equals 97 or lower. And these areas are identified with the blue arrows. So As we proceed with our detective hat on, we ask, what proportion of all possible random samples of size 25 have means that differ from the hypothesized population mean by at least as much as ours seem to? First, we standardize the points of interest, as we always do, by converting them to z-scores. Our formula is x bar, or the average of our sample mean, minus mu, the population mean. Divide that by the standard deviation of the sampling distribution. Let me give a reminder here. We're looking at the standard deviation of the sampling distribution, not the particular sample of interest and not the population standard deviation. The standard deviation of the sampling distribution is the one we've been calling the standard error of the mean. A z-score for the value 97 is equal to 97 minus 100 over 3, and that's equal to -1. A z-score for the value of 103 is 103 minus 100 divided by 3, and that is equal to +1. Where are the samples whose means differ from the hypothesized population mean by at least as much as our samples seem to? They live in the areas near the tails of the distribution on both the lower and positive sides marked by the blue arrows, and we know from our study of the z-score tables that these areas comprise proportions of 0.1587 of the distribution below the mean and 0.1587 of the distribution above the mean. So, to recap, what proportion of all possible random samples of size 25 have means that differ from the hypothesized population mean by at least as much as ours seem to? We find our answer by adding the two proportions of 0.1587 together to find the answer that shakes out is 0.3174, or 31.74% of the samples of size n equal 25. So now we have a few intriguing questions that we must answer to get a full understanding of what we found. Did we observe the ideal outcome? No, we would have preferred something closer to 100, or even 100 itself, to satisfy our hypothesis that the mean of the population equals 100. Did we observe an unusual deviation from the ideal? About a third of the observations would fall in the area that houses sample means that are less than -1 standard error or more than +1 standard errors above the mean. Is 1/3 an unusual occurrence? I would argue that it's not especially unusual. For example, if you lived in a place where it rained 1/3 of the days of the year, so about 4 months of the year, and you stepped out of the house one day and it was raining, would you be shocked and amazed? Would you say, "What is this strange wet stuff falling from the sky?" Probably not. You'd simply grab your umbrella, say, "Oh gee, another rainy day," and be on your way. Should we attribute the deviation to random sampling error? If you hypothesize that a population has a mean of 100, and the sample mean that pops up from your sample is 103, it would be safe to say the hypothesis is supported, because 103 is not a terribly unusual event, and I would say it's likely due to sampling error. Should we conclude that the null hypothesis is true? We can conclude that the data support the hypothesis and that the mean of the population is equal to 100. Now, for a bit of context, the tradition in the world of statistical hypothesis testing for an acceptable level of discrepancy has been set at 5%. This works out to 5 chances in 100 or 1 chance in 20. This criterion says that the level of significance of our test is 5%. So the occurrence of a score of 103 is more likely than 5% and would not be considered a significant difference from 100. In contrast, an event that is likely to occur less than 5% of the time is considered unusual, and we also call this significantly different from the test mean of 100. We'll go in more detail on the concepts of significant or not significant in the chapters ahead. And then we have to ask, might we be wrong in our conclusions? Of course, we can always be wrong in our conclusions from our statistical tests. And I want to emphasize this point. Often, as researchers, we become too enamored of our hypotheses, and as practitioners, become too attached to our hunches. When the data are not consistent with our hypotheses and hunches, we often will discard the data and persist in our beliefs. So I like to encourage researchers and practitioners to learn what I call empirical humility. In other words, accept the fact that your hypotheses and hunches can be wrong. So let's try another one. The null hypothesis is that the mean of the population equals 100 and the standard deviation equals 15. We take a sample and we find that with a sample with 25 people in it, the mean is equal to 88. Where are the samples whose means differ from the hypothesized population mean by at least as much as our sample seems to? Just as we always do, we draw a rough sketch of the distribution and label the mean of the sampling distribution, which you recall is the same as the mean of the population. We then identify the point on the distribution that is below the mean of 88, so 12 points from the mean, and by symmetry, the point that is 12 points above the mean, so 112. The sample means of interest are the ones that dwell in the two areas indicated by the blue arrows. These sample means are at least 12 points from the mean of 100. So, what proportion of all possible random samples of size 25 have means that differ from the hypothesized population mean by at least as much as ours seems to? We answer this question by first standardizing the points of interest, 88 and 112. We find the z-scores associated with these points of interest are -4 on the low end and +4 on the high end. Where are the samples whose means differ from the hypothesized population by at least as much as our sample seems to? So we answer this question by consulting our z-score table from a few lessons back to find the proportion of sample means in these extreme ends of the distribution. And the proportions are 0.000032 at the low end and 0.000032 at the high end. So to recap, what proportion of all possible random samples of size 25 have means that differ from the hypothesized population mean by at least as much as ours seems to? And the answer is found by adding up the two proportions together, and the result that emerges is 0.000064. So clearly, the probability of this event is very, very low. So, did we observe the ideal outcome? No, we'd like to find support for our hypothesis, and this would require a sample mean much closer to our hypothesized mean of 100. Did we observe an unusual deviation from the ideal? Yes, this is a very unusual sample mean if we imagine that it had been drawn from a population with a mean of 100. Recall in a prior slide I said that the standard for an unusual deviation for the ideal is an event that is likely to occur less than 5% of the time. An event with a probability of 0.000064 occurs less than 0.0064% of the time. This event clearly falls in the group of events that occur less than 5% of the time. So should we attribute the deviation to random sampling error? Well, I'm not comfortable doing that. A score of 88 or 112 is probably not due to a random sampling error. Should we conclude that the null hypothesis is true? I would conclude that the null hypothesis is not true. I would reject the null hypothesis in this case. And here again, we have a hard time letting go of our precious hypotheses and rejecting that hypothesis. But this is the safest route in this situation. Might we be wrong? Yes, in the world of probability, there's always the possibility that we're wrong. It's possible to draw a very unusual sample with a mean of 88 or a mean as high as 112 simply by chance from the population. If the population mean is 100, it's very unlikely, but it's possible. Very unusual events sometimes do happen. So we've come to the end of Chapter 11, Unit 3. Our next unit is level of significance, and then we'll look at critical values, critical regions, directional tests, some more examples, and then errors of inference.